The talk today is going to be on phylogenetic or phylogenetic analysis on inapplicable characters. I'm going to go quickly through this. The general organization for this lecture is going to be in two parts, theory and practice. And in the part on theory, first I'm going to do a quick review of the literature, which helps me, structure the talk and follow a specific sequence, showing you how the arguments were made in regards to inapplicables. And then I'm going to do the methodological aspect of the methods and algorithms using TNT. Then we're going to move to the more practical part, checking the syntax for specifying inapplicable characters in TNT. And then we move on to the examples, onto the computer program, using the computer program itself, which, as I was telling Amrita, I expected that would be the most chaotic part of the talk, but I was saved by the circumstances. There was something worse. Okay, so first we're going to do a literature. We're going to travel through the main papers that have been have dealt with inapplicable characters. So we move on to that. These are the most important papers. Some of them I'm going to go through very quickly, others not so much. The most important paper is the one that Fares published in 1983. He laid out the basic foundations for doing phylogenetic analysis, at least in terms of the justification that is used for analyzing inapplicable characters in TNT. What Fares did in that paper is examining the logical relationship between evidence, conclusions, and explanatory power. And he considered in that paper that phylogenies, or genealogies, are devices that allow us to understand observed similarities as a result of common inheritance. That is, a phylogeny allows understanding, which is to say, making sense of why some species share a similarity. You observe a similarity, then you want to try to explain why those species are similar in sharing that character. Better phylogenies then are those that allow understanding more similarities as the result of common inheritance. When you attribute a similarity to common ancestry, that amounts to considering that similarity as due to homology, by definition of homology. So you can also say that optimal phylogenies are those that allow considering as homologous the largest possible number of similarities. Fares showed in his paper that for a single character, placing the similar species in groups with single origins allows attributing their similarity to common ancestry. And the fewer groups in which you split the similar species, the more similarities you can explain by common ancestry. Therefore, the number of independent originations of similar features, that is to say, steps, is in inverse relationship to explanatory power. So let's look at some examples. If we have this tree, we have some taxa. Can you see the mouse moving, Amrita or Santi? Is the mouse visible?
Yes, I can see. I can see.
Okay, so the pointer is visible, fine. So if we have some species with a red color, some species with a blue color, so the thing we want to explain would be why the species P, Q, R, etc., all the red ones, why do those share the color red? That's the thing we want to explain, the observation we want to explain. And given this tree, we can answer because they inherited the red color from a common ancestor. It's as simple as that. So this tree allows explaining the similarity in red color, and explaining, that is to say, understanding, is what we want to accomplish. So that tree serves our purpose of understanding similarities in terms of common ancestry. Note that we say allows, we don't say requires. The tree is still compatible with other reasons for the similarity. The similarity might be something like this in truth, right? But even if the similarity is really due to a bunch of parallelisms, we can still use this tree to understand that similarity as if it was due to common ancestry, even if it is not. In other words, the tree allows understanding similarities as homologies, even if they are not. This is crucial in terms of the justification for parsimony, because a lot of discussion centers on whether character states are really homologies, and you cannot know that ahead of time. The tree is the device that allows you to think of the maximum possible number of similarities as if they were homologies, even if they are not. But the tree you use to explain observations. And one more thing is that, of course, blue and red are always homologs, because any red you are going to have in here is going to be, in some part of the tree, a transformation from the original blue. So you have homologies at two levels. One is that the red and the blue are always homologs, and you decide that when you put that as a single character in your matrix. But the reds being red at the level of character states, that is what the tree can help you interpret better or worse. And of course, you want the trees that allow you to interpret that as well as possible in terms of common ancestry. If you place the things that have red color in two separate groups, then the similarity in red cannot be explained in terms of homology now. So XYZ can be explained, their similarity can be explained as due to homology. The similarity among all of these can be explained in terms of homology, but any combination of XYZ with any one of these Q, R, P, etc. cannot be explained as due to homology. Note here the problem of the non-independence of those comparisons also, because if X is a homolog of Y and X is a homolog of C, right? Once you know that X is not a homolog of, say, P, it follows that P is not a homolog either of Y or C. So those are not three independent comparisons. Just one comparison is independent there. And the thing that really tracks the number of independent cases of similarities not explained as common ancestry is the number of originations. Now, if you really want to believe that the red color is homologous in all the taxa, you can force that interpretation in the tree by doing something like this. But that now failed to explain many more similarities. You cannot explain by common ancestry the similarity between N and OJ or between N and L, etc. So, overall, this is a better explanation, which is also happens to be the one that requires the fewest independent originations of similar features in the tree. So one more thing is that both blue and red are equally important. It's not that we want to explain red preferentially over blue. In principle, all characters and states will have similar weights. It's up to the user to decide if there are grounds for doing something else. In this tree, instead of two, there are three independent cases of unexplained similarities, three different originations of the red color. And on this tree, no similarities in red color whatsoever can be explained by common inheritance, at least not unless we give up on explaining the similarity in blue color for even more cases than there are red. I'm getting a sip of water. Sorry. So it is clear that the ability to explain similarities by common ancestry decreases with numbers of steps. In a tree and ancestral reconstruction, all the taxa that are connected by ancestors having the same feature owe their similarity to homology. For every independent origination, that is to say a step, all the taxa and ancestors directly connected to that origin are then homologous. Note that the focus here is on explanation of observed similarities, not on steps. There are some formulations of parsimony that center on minimizing events, as if events, the originations themselves were the things that we want to minimize. That was certainly not Farris's position. One could say that parsimony is not a model of evolution, it is a model of knowledge. What it's trying to quantify is not how evolution has actually proceeded. What it is trying to quantify is actually what we can do in terms of how we explain the observations, how good the explanation we can provide is given this tree or that tree. So it's a different approach from, say, maximum likelihood. As the focus is on explanation, of course, that explanation needs to be legitimate and consistent. That is, it needs to agree with other things we know about evolution, about development, and so on and so forth. For example, if a tree requires fewer independent originations, but does so by virtue of postulating ancestors with stop codons in the middle of a gene that codes for a vital protein, we know that such an ancestor could not have existed. Then that explanation is not a very good one. You have to be careful with the kind of explanations you do if you have some additional knowledge of what counts or doesn't count as a possible explanation. And Farris completely allows for that, even if somewhat indirectly in his paper, but he discusses things that are clearly connected to this idea. Now, a small digression on terminology. Parsimony, in Farris's view, is called parsimony because it minimizes the hypothesis ad hoc. A hypothesis ad hoc is not really a scientific hypothesis. I don't know why they call it that way. That's, common usage, but rather a hypothesis ad hoc is something which we postulate with the sole purpose of defending a conclusion. Defending a conclusion that is against observations that would otherwise falsify the conclusion. That is to say, homoplaces. So if a similarity that we have observed and seems to be prima facie, one would say, evidence of common ancestry, requires several steps on the tree, if that similarity were truly due to common ancestry, then the tree would be false. So we have to reject the idea that the similarity is due to common ancestry if we want to retain that tree. That rejection is what counts as a hypothesis ad hoc. So in summary, Farris in 1983 gives a justification for preferring phylogenies that allow explaining more of the observed similarities as a result of common inheritance, and that amounts to choosing phylogenies that minimize the steps required to account for the data, and that amounts to, by definition, to choosing phylogenies that maximize homology. Remember that I said the trees can explain some similarities as homologies, even if they truly are not. To the extent that you can explain observations, it is that you begin to think that that explanation becomes true. The more observations you can explain, the greater the confidence that you have that your hypothesis is correct. The way Farris put that in another paper in 1982 is that scientific hypotheses are not used as explanation because they are known to be true, but they are thought to be true precisely because they provide explanation. So it's important to keep all of this in mind when we are thinking about inapplicable characters. So given a tree, the optimal ancestral reconstruction follows, regardless of how we find it. It simply follows from what we have been discussing so far. When you think of Fitch, Farris, or Sankoff or step matrix methods for optimization, those are simply tracking methods, right? Calculation devices, if you want to call them that, for finding optimal reconstructions more easily. But the optimal ancestral reconstruction follows from the costs of transformations between states, which represent preferential homologization of one or the other state. Those algorithms, Fitch, Farris, or step matrix algorithms, are conceived for working on a character at a time, one at a time, and then characters are assumed to be independent. You simply sum up the scores for all the characters and you have the overall evaluation of the tree. Now, this might be a point to do a break or questions. I don't know if people have been asking questions. The moderators are going to channel those. Santi, how am I doing? Shall I continue? Amrita?
No, I think you can continue for now. Yeah.
Okay. Okay. Okay, so in 1993, that's, we were in 1983, 10 years later, Madison came up with this problem. He introduced the problem of this is getting repetitive, inapplicables. And he considered some problems that arise when you simply apply standard algorithms to the analysis of inapplicable characters. What are inapplicable characters? Well, suppose you have an example such as this. You can have some lizards, some of which have a red tail, some of which have a blue tail, and other lizards have no tail at all. In those lizards where there is no tail, you don't know whether the tail is red or blue. In the situation posited by Madison, then, the character tail color simply does not exist when there is no tail. The character tail color only comes into existence, so to speak, when the tail appears, or ceases to exist when the tail is lost. The two options that you have for coding such characters when you have standard methods were discussed by Madison. One is reductive coding, where you are going to code the taxa which lack a tail. That would be the first character 0. So A, B, C, D, lack a tail. Then you don't know what the color is. You score that as a missing entry. Then you score the taxa, that have a tail with the color that represents whatever, blue, and then the other taxa that have a tail with the red code that represents red color. The other possible coding that Madison discussed is the non-additive coding, which you do with a Fitch optimization, which is you use one state for representing the taxa that lack a tail, you use another state for representing the taxa that have one color, say blue, and you use another state for representing the taxa that have a red color. So those are the main options that Madison analyzed. If you check what happens with reductive coding, some paradoxes arise. Because remember, that would be two separate characters, right? So if you have this tree, the black color here indicates presence of tail. The tail here would be evaluated as having two steps. There are two independent originations of the tail. And the color would have one step. You really have no connection if you think of what's really happened, because these branches in here lack tails. But when you apply Fitch optimization always assigns some states to the ancestral nodes. So you need to have some steps somewhere in the tree, in the path that connects the blue taxa and the red taxa. So this tree is going first. It's going to have some color of the tail assigned to ancestors that really have no tail, which makes no sense. And it's going to have a total of 3 steps. Remember, we use these scores to select from among possible trees as our preferred phylogenies. Now, consider a different case, again with reductive coding. Suppose that you have split the taxa in this way. Now, this is also going to have 3 steps. You have 2 steps in the tail, and you have 1 step in going from red into blue here, right? But even if you have 3 steps, exactly what you had before, this tree is really not the same as before, because the taxa with red colors are separate in 2 parts of the tree. The way in which we can explain the similarity in red color given this tree is not as good as before. Yet we have the same score for evaluating the tree when we are doing reductive coding. Even more, if you switch to this tree now is going to have 4 steps instead of the 3 we had before. But this tree is, in a sense at least, exactly the same as before, because the taxa with red color are separated in 2 parts of the tree. All the blue ones are in just one group. So this tree is evaluated as being worse than the previous tree, but it is really the same as the previous tree. So you can see 2 different ways in which reductive coding can screw up in the analysis of inapplicable characters. The other alternative is considering the character as considering these 2 characters as a single one, a non-additive character. Suppose you have the taxa with blue and red tails sitting side by side on a tree. How are you going to reconstruct this character if it is non-additive? Remember that non-additive means that all transformations between all possible states have the same cost. In that case, for this node, you can assign, or you can think of a no tail transforming into a blue tail in this node, and then into a red tail, which will imply 2 steps. But you can also think of a no tail transforming into a red tail, and then into a blue tail, which is fine. It's again 2 steps. But you can also think of this intermediate ancestor as having no tail, and then a blue tail originating on one side of the tree and a red tail separately originating in the other branch. Now, this also has 2 steps, and this means that the homology of the tails themselves is not being registered, so to speak, by this coding. So if you take the blue taxa and the red taxa and you put them into separate parts of the tree, now you force this interpretation. You have 2 separate originations of tails, one of which is blue, one of which is red, and you have exactly the same number of steps. So these 2 trees with non-additive coding would be considered as equivalent, but clearly the trees are not equivalent. They do not have the same explanatory power. One tree allows to understand the presence of tail as resulting from common ancestry, the other doesn't. So Madison, in his paper, discussed the question that in special circumstances, the long-distance interaction of tail regions of the cladogram may actually be desirable. One might want the reconstruction of tail color evolution within the basal tail group and the secondary tail group to influence each other across the intervening tailless regions. He's referring here to, I'm going back some slides, to this which happens here, right? Those would be the intervening regions that Madison is talking about. One might want that, sorry. So one might want those groups to influence each other across the intervening tailless region, if it is thought that the character was most likely to reappear as it was just before its loss. For example, the genes coding for color and tail presence are completely separate genes, so the tail can get lost, but the genes that code for the color of the tail continue being there and are unmodified. So in that case, the expectation would be that if the tail reappears, the tail is more likely to have the same color it had when it got lost, just as it happens with reductive coding. So in that situation, the color character is not inapplicable or unobservable when the tail is absent. It is just unobserved. So nothing prevents us from sequencing the genes that code for tail color and find out the color that those genes code for. right? So the character is not truly inapplicable in that situation. Jumping some years forward, Goloboff et al. 2021 called this the hen's teeth hypothesis, or HTH, by reference to the fact that birds, even if they don't have teeth, they seem to retain the genetic machinery needed for building teeth during development. So inapplicable, when you say that the character is inapplicable, you are presupposing or assuming that this is not the case, right? Because if you can think that the genes determining what happens with the parts continue being active and potentially can be sequenced, right? That is not inapplicable. That's a reductive coding. If the character is truly inapplicable, those are the cases Madison was referring to and the ones we discuss here. But whether or not the character is truly inapplicable, or you can think of the hen's teeth hypothesis, is an empirical statement. It is up to you as a user, as a researcher, to code or think of your characters as faithfully as possible. So, for truly inapplicable characters, the situation is, this is summary, the reductive coding can attribute color to ancestors that are reconstructed as having no tail and allow separate regions of the tree having tails to interact, with which it can consider as identical trees that should be evaluated as being different in terms of their explanatory power, and can indicate differences in trees that should be evaluated as identical. If you instead choose a non-additive coding, you do not recognize the homology of the tails. And it has the additional problem that if you have many dependent features, not all changes can cost a single step, because we were discussing just a tail that can be red or blue, right? But suppose that not only can the tail be red or blue, it can be wide or narrow, it can be long and short, and every one of those combinations of differences, is that going to cost a step? That is simply something you cannot record by using a non-additive character. The solution Madison, or a potential solution Madison proposed for this, was to use a step matrix recoding, where you consider all combinations of states. So this would apply algorithms for step matrix optimization. The idea that Madison was proposing here was that the systematist may want to assume that gains of a tail are more important and tend to delimit larger monophyletic groups within which a secondary and less important character, tail color, delimits substructure. Gains and losses of tails could be weighted more heavily than changes in color if step matrix algorithms are used. Note here that Madison is no longer let me get some water, sorry. Madison is advocating here the idea that some of the characters are more important than others and they should be upweighted. And that's why he proposes to use step matrix algorithms. He also noticed that if many more distinctions among tails are found, in addition to the color, that is, for example, long and short, bumpy or smooth, etc., it may not be possible to fuse all the characters, more properly one should say the character state combinations, in existing computer programs, because the resulting character could have hundreds of discrete states. That is to say, tail red and hairy and short and smooth and twisted versus tail red and hairy and short and smooth and coiled versus etc. etc. Even if the program could handle a character with so many states, the calculations with it using its large step matrix would be unbearably slow. So this is a problem that Madison pointed out in '93, and it is a practical problem, not a theoretical problem. He also said that lacking evidence to indicate the relative weights, the particular number of steps assigned to each change is going to be somewhat arbitrary. If an extreme weighting were chosen, for example, 100 steps for gain loss of tail and only 1 step for change of color, then this would have the effect of choosing a reconstruction that minimizes the number of gains and losses, and secondarily within those areas of the tree with tails minimizes changes in tail color. Some systematists might find giving primacy to gains and losses desirable. However, when achieved with an extreme step matrix, changes in tail color then would contribute relatively very little to choice of trees. And this would be a theoretical problem of applying step matrices in Madison's view. Okay, so this is a summary of Madison's 1993 paper. It was a pretty good paper, especially considering the times. Madison at the time had already programmed McClade, so he knew very well how algorithms for optimization work. He had a pretty good understanding of phylogenetics. So the paper, even if it has some problems, it clearly shows what the problems are and what the problems are with potential solutions. Hawkins et al. And Liam Bryant and Strong and Lipscomb and Forey and Kitching in the few subsequent years after Madison, several authors got interested in the problem of inapplicable characters and starting publishing their own views. Really, none of these papers adds much. Madison's paper still continues being more interesting and clear than all these ones. I'm not going to go through those in detail. Then the problem was, at least in theory, solved finally by a paper by Ian Delet in 2005, and he also published another important paper in 2015. And he reanalyzed the problem of inapplicable characters. It is the first paper that proposed to go back to the basics rather than starting from existing algorithms for phylogenetic analysis and try to fit those algorithms into handling inapplicables. He started by discussing the basic goals of phylogenetic analysis, which is take into account Farris's ideas. So what he proposed is that one should try to maximize homology. Instead of thinking of specific algorithms for reconstructing characters, you have to think of how homology is or is not being maximized by different reconstructions. Delaet's paper is very technical and very difficult. Most people, myself included, failed to understand that paper for a long time. So it is a paper that did not have a very strong impact in the field, especially in practical terms. And it's mostly because people were actually missing the implications of what the things that Delet was saying. And to make things worse, the paper is a book chapter. It doesn't have an abstract. Abstracts serve also to, give you summaries of what the main ideas of the paper are. There is no such abstract in the paper. The paper is lengthy and discusses every aspect of phylogenetic analysis. So what Delet, I was checking the paper right before when I was preparing this talk, and I confess, you really have to read a lot to go to the real substance of the paper. It's really hidden in there because Delet is very, very detailed. He discusses all the alternatives, all the implications, but that makes it for hard reading. What he did was he proposed a way to keep track of the homology in a joint reconstruction of tails, colors, and other dependent characters by counting 3 things: the number of transformations in the main character, the number of transformations for secondary characters in the regions of applicability, and the number of distinct regions of the tree where each character is applicable, which he called subcharacters. The optimal reconstruction, that is the reconstruction that maximizes homology, is the one that minimizes this triple sum, that is those three quantities together. Now, the Let's papers are purely theoretical, and he later implemented his ideas in an experimental computer program called Anagalis. That program, Anagalis, finds reconstructions and trees that minimize the sum of those three quantities. And all of this is correct, but it is way too abstract for us normal human beings. I would have a hard time explaining why those three quantities really minimize homoplasy and how you go around measuring them on specific trees. So it's difficult to get that from the paper, but something that Delet understood perfectly well right from the start, and I finally understood this in conversations with him many years after he published his paper, is that in two independent originations of a tail with the same color, neither the tail nor the color can be considered as due to homology. And I think this is the most important aspect of the problem that most people were missing before. That is, when two tails of the same color originate in two different parts of the tree, there are two instances of homoplasy, that is to say, unexplained similarity, what we want to minimize. One of those instances of homoplasy is for the tail, the other is for the color. Now, if you count the number of words in this slide, this slide has 63 words. And as you all know, a picture is worth 63 words. So let's see some examples. Remember these trees, which look the same under reductive coding, they were evaluated as being the same. Are they different? Intuitively, we said that they were different, but how are they different based on Delahaye's reasoning? Well, this tree would have one step of homoplasy. All the things that have the red color have that red color by virtue of homology. Instead, in this tree, you have two steps of homoplasy. One step of homoplasy corresponds to the tail. Why do these two groups have tails? It's not because of common ancestry, so that's homoplasy. But if you ask why any one of these taxa has red, and why is that similar to the red color in this group, that is homoplasy. Because if you have no tails, you cannot explain, you cannot attribute the presence of a red color. So you need one, say, origination of the red color here and one origination of the red color here. So these two trees look the same under reductive coding, but clearly on the Let's criterion, they are different. Now, one important thing is that reconstructions are not given. You need to evaluate the reconstructions on the basis of their homoplasy. And the only way to do that is by considering all characters jointly. You cannot do that by considering the characters one at a time. If we take that same tree and count the homoplasy on this reconstruction, that requires two steps of homoplasy, because we have the tails, not due to common ancestry. We have the red color, not due to common ancestry in the two groups. You could reconstruct the ancestors as having a tail, and that tail is red. In that case, you can explain the shared presence of a red color in this taxa by common ancestry, as well as the presence of a tail, of course. But then you have three steps of homoplasy, because now you are failing to attribute to common ancestry three separate instances of a tail. So this reconstruction is going to be worse. This reconstruction is preferable given these three and these characters together with their interaction. Which reconstruction is going to be preferable is going to depend on the number of characters that are dependent and whether or not they agree in the independent originations. Suppose you also have the section of the tail in addition to the color of the tail. So if the red tails are all squared, the blue tails are all rounded, in this case, you have 3 steps of homoplasy. Why do these things share a tail? It's not common ancestry, that's one homoplasy in the red color, one homoplasy in the squared section. This squared section is not being attributed to common ancestry in these 3 in the left. You could now reconstruct the characters so that you have a tail, and it's a red tail, connecting those things, and that tail is also squared. In this case, you have 3 steps of homoplasy. So this reconstruction is now ambiguous. Now you can see that whether or not this ancestor is optimally reconstructed as having a tail or not is being influenced by whether or not the tails are squared or rounded. That's because that's the reason why we say that the characters are interdependent. Okay? Now suppose we go even further. You have one more character, the pill let's say hairs. Enough about pills. So you add one more character. In this case, these independent originations of the tail, sorry, there was a problem with power. You're still hearing me?
Yes,
We can
Pablo.
hear you.
Yes.
Okay. Yeah, I had a little blackout of my lights in here. Okay, so if we have 2 independent originations, this fails to account by common ancestry for the independent, for the similarity in tails, red color, section, and hairs. So this reconstruction here has 4 steps of homoplasy, while this reconstruction here continues having 3 steps of homoplasy, right? You have a tail in here, and this is not due to common ancestry, neither is this, neither is this. There are 3 independent cases of absences of tail that are not due to common ancestry. So you can see that the number of dependent characters influences how the tail is going to be reconstructed when you take into account the homology. Now, does that mean that it is always going to be preferable to consider that sorry, I'm trying to get the pointer of the mouse. The tails are always going to be preferably considered as homologs as tails if you have more dependent characters? No, not necessarily. If the tails that originate separately are all different, this one is red, rounded, and scaly, and this one is red, squared, and hairy. And this has only 1 step of homoplasy. Where is that homoplasy? Now, I don't know if I'm going to get 150 people saying, in the tail, but that's where the homoplasy is, right? That's 2 independent originations of the tail. In this case, if we reconstruct such as this by assigning a tail of some color to the common ancestor of those 2 groups having tails, the only thing we can now explain by common ancestry is the presence of the tail, because there's nothing else to be explained. There are no more further similarities. So we have the 3 steps of homoplasy in the tail losses. So this reconstruction in the left is clearly preferable to the one in the right when you have independent originations of tails that are very different. Okay, sorry, that's the mark there. Those are the 3 steps of homoplasy marked in the right, and the single case of homoplasy in here. So this is the basic idea in the late 2005. A given reconstruction can be evaluated by the triple sum if you want, but the problem of how to find the reconstruction that truly minimizes the triple sum is left open in the paper. He does not discuss specific algorithms. We were just counting by hand in the previous cases, but that is clearly not something you can do in a real phylogenetic analysis. And those algorithms are what he implemented subsequently in the program Anagalis. But the algorithms themselves are unpublished. The Anagalis is not open code, and the algorithms are complex, applicable only to relatively simple case and rather slow for cases with many taxa or much homoplasy. Okay, so we were just discussing the let's ideas. I mean, the idea that what you have to do for analyzing inapplicable characters is exactly the same thing you do for analyzing standard characters, which is find reconstructions that maximize the degree to which you can consider similarities as due to homology. Sorry for the long sentences, but that's the way it is. Okay. And that maximization of homology for the characters that have inapplicabilities, that is, have some kind of dependence, that has to be done in terms of the original characters. Now, following the let, there was a couple papers which may be worth looking at because some people either made discussions of the let or published alternative criteria or alternative methods. One was the papers by Kluge and Grant, 2006, and Wheeler in 2023. They refer mostly to this kind of problem. They say, okay, consider that you have 5 sequences, right? One is N is ATGGG, the second is ATG, and you could align those sequences in this way, such that every actual state observed is unique. This, which is at the bottom, is the minimum possible number of steps because they were giving transformation from a gap into a sequence a cost of 1. So the minimum cost of everything is 1. And then on a tree, you can account for those data with 25 steps, which is the minimum. So in a sense, this has no homoplasy, they say, because the number of steps you can have on a tree, on any tree actually, equals the minimum possible number of steps. Now, this is the trick. It can equal the minimum possible number of steps in the data which are already aligned. And Kluge and Grant and Wheeler say, instead, in this case, you have no gaps, right? And you have one instance of homoplasy in here, right? A she transforms into a C, and then it goes back into she. So this has fewer steps, right? But has some homoplasy. So if we are going to choose, they say, to choose trees based on minimum homoplasy, you would be preferring, sorry, I'm going back, you would be preferring this one on top, which is absurd, and it requires 25 transformations. The one on top requires only 5 transformations, but there is some homoplasy in there, they say, okay? So what we need to do is minimize transformations, not homoplasy, okay? And they say that the minimization of homoplasy cannot be used for the analysis of inapplicables and DNA sequences in general. The response by the lead, which is in that paper in 2015, was no, not so. The counts really are being incorrect. That is not what I meant. The number of characters themselves must be counted. Remember that he spoke of counting the regions of inapplicability. The originations, so to speak, of characters themselves needs to be counted, and you can have or not have homoplasy in that. That is, you need to account for the homology of positions. On that criterion, which is precisely what the Laet was proposing, the first example is indeed way worse, as expected, as it should be. So you really prefer the second example using the Laet's criterion, not the first one, as Grant and Kluge would have it. Another paper that published some considerations about the analysis of morphological characters and also inapplicable characters was by Brassot, 2011. He did not cite the paper by Delet, perhaps he had not read it at the time. This is a well-cited paper. And he also considered the possibility of Sankoff optimization, but he said that one has to be cautious of weighting character transformations and proceed very carefully. You can read the entire thing, but basically he continued being skeptical of the step matrix approach, pretty much based on the same reasoning of Madison, because Madison said, well, one could use step matrices, but exactly what should the rates between transformation costs be? How much cost we give to tail gains and losses? Then you have another paper about which there isn't much to say by Hopkins and Sanchon, 2021. They really did not consider the let at all. They confuse actually the let's proposal with favoring trees that group characters into regions of homology. That's what they say that the Laet proposed. The Laet never proposed that. I really don't know what they mean, because the Laet did never speak about grouping characters into regions of homology. So I'm not sure what they got from the paper. The main idea in Hopkins and Sanchon is that the more characters that depend on the same primary character, the lower the weight of those dependent characters must be. So if you have a tail that can have a red or blue color, that color should have a weight, say, of 1. But if in addition to the color, you can also have a section that is squared or rounded, each of those should have a weight of half. And if you now count the hairs or the scales, each one of those characters should have a weight of 1/3. But why? Because if there is conflict, if there are some groups determined by having, I don't know, a red color in the tail, in principle, that red color should have exactly the same weight as every other character in the matrix, at least if you are not applying some weighting method. So in principle, you should be able to deal with all of the characters having the same weights or costs. The first algorithm proposed for handling inapplicable characters was by Brassot et al. In 2019. And they did cite the let. They do say that they wanted to maximize homology, but they propose a method which is really not guaranteed to maximize homology. And they say in their paper that further work will be necessary in order to compare the results of this analysis, that is using their method, with those of exact methods, such as the LET's forthcoming Anagali's program. The proposal by Brassot et al. Is you optimize the primary character first, and then, subsequently, the dependent characters, but only in those parts of the tree where the primary is present. This, indeed, avoids the problem of mutually incompatible ancestral state assignments, right? But the problem of score remains. Remember that I said when I was showing the examples from the perspective of the Let's criterion, the optimal scores can be obtained only when all the characters are considered simultaneously, not one at a time. You cannot look at the tail first and then later at the other characters. You have to look at all the characters at the same time. Therefore, this method can produce suboptimal reconstructions and miscount homoplasy. Remember this case where we have the tail can be have a red color squared section and have hairs, or be blue, rounded, and scaly. And this reconstruction has 4 steps of homoplasy, while this reconstruction has only 3 steps of homoplasy because it allows considering the red and the squared and the hairs as inherited from a common ancestor. Therefore, this reconstruction is preferable. But if you look at only the tail, you are going to map the tail on the tree in this way. So Brassot et al.'s method chooses this reconstruction, which has 4 steps of homoplasy, instead of 3, which is the minimum you can have given these 3 unoriginal characters. So that would be a problem. This is exactly what Delahaye responded in 2019 in a paper which was not peer-reviewed. He gave examples of that. And we also gave examples of those problems with Brassot et al.'s methods in our paper in Goloboff et al. 2021. Another paper that dealt with the problem of inapplicable characters was the paper by Simons et al. In 2023, but they only did simulations using Fitch method, Brassot et al. 2019, and Hopkins and Sanchon's method. Remember the one that lowered the weight of multiple dependent characters. He did not consider Tarasov, 2019, which is a method for handling inapplicable characters and the likelihood. We are not considering those in this workshop. We could do that in some other workshop, but that's a lot more stuff, so I'm focusing on parsimony only. And they did not consider the method we proposed in 2021. And the only, so to speak, theoretical argument in Simons et al. Is a really serious error. Really problematic. It does not make any sense. If there are questions on that, I can answer them. So we should move on to part A2, the maximization of homology and the methods used in TNT. So how does TNT go? How can TNT go about actually maximizing homology when you have inapplicable characters? This is a paper we published in 2021. As you can see, Ian Delet is a co-author. When I was trying to implement some methods for inapplicables in TNT, I exchanged a fair number of emails with Delet, and it's only then, in 2020, which I could really understand the point he was making, okay? It took me many, many years to understand his paper. We try to explain that more clearly in this paper that reconsiders the problem. Hopefully it is more clear. I remember that when I finally understood the idea, Delahaye wrote an email to me saying, Pablo, you are the first person ever who can understand what I meant. Hopefully after this workshop, there will be lots of people who understand what Ian Delet was meaning, but we'll see. And then we published the sequel together with Ian Delet on incorporating other types of dependencies, but the syntax for specifying inapplicable characters is the one in that paper. So those two are two important papers. In the 2021 paper, we reconsidered then the problem of inapplicables. And what we did was use Delet's criterion of maximizing homology, and this is Farris's criterion of explanatory power. Not the specific algorithms, the criterion of considering what should a genealogy do, maximizing explanatory power. And we reframe that. The methods we propose there produce exactly the same results as Delet's method and Delet's program Anagalis, except that they are formulated differently. It's just a different way to calculate the same thing. And these are the first papers proposing actual algorithms to find reconstructions of maximum homology for dependent characters, because, like I said, the algorithms for Anagalis are not published. Rather than the triple sum, which Delet proposed, one can track the homoplasy for reconstruction on a tree with the number of cases for each individual state and character where a state originates from something different than that state, the root included. And then, if you have several originations, you subtract 1 to that number and you have the homoplasy, which is exactly what Farris was proposing homoplasy is in 1983. And we call these X transformations, transformations between the minimum possible. Then, the reasoning of Farris 1983 can be used for inapplicable characters, exactly as he proposed it, basically, except by a small reformulation of the problem. So let us consider the trees we were looking at before. So if you want to apply that here, you would have to count what happens for the tail absence, the tail presence. Tail absence, there is just one quotes origination at the root. And then there is no case of a tail being absent when its ancestor is not absent. How many cases are there of a tail being present and the ancestor not having tail? There are two. You subtract one and you have one case of homoplasy in the tail. So the total for blue, there is just one origination from something that does not have blue. If you subtract one, that's a homoplasy, that's 0. Same thing for red, 0 and 0. So the total homoplasy for this tree is one step of homoplasy. If instead you look at this tree, there is no homoplasy for the tail absence. There is one homoplasy for the tail presence. There are two tails which are present from something that was different. And likewise for the red color. So this tree has two steps of homoplasy. That's the exact number. So with X transformations, you can evaluate any tree or any reconstruction. This one has two steps of homoplasy, which is what we had intuitively counted before. One for the tail, one for the red color. This reconstruction instead has three steps of homoplasy. Those would be three cases where the tail is absent, right? And the ancestor did not have an absent tail. So that's three originations, three extra originations of the tail, right? When you have more characters, you have to count all the characters and state independently. So you come up with a total of three steps of homoplasy when you have two tails with two dependent characters in identical state originating twice. And you have three steps of homoplasy if you count just one origination with three losses. That would be three absences of the tail. And these two reconstructions are equivalent, which is what we had concluded before. If you add even more characters, you are now the vestiture, whether they have hairs or scales, right? So this reconstruction would have four steps of homoplasy. While this reconstruction, assigning a tail that is red, squared, and hairy to the common ancestor of the red things, implies only three cases of homoplasy. None in here, those are in the tail, which I listed before. Note here that assuming the weights given by the user to the characters are all unity, the failure to homologize a tail absence or presence and the failure to homologize any of the dependent characters are penalized exactly the same. Just one step of homoplasy for each of those cases. There is no preference for homologizing tails over any of the dependent characters, or any preference for homologizing presence over absence. Contra Madison 1993, you don't need to have that in order to be able to deal with the problem of inapplicable characters. And this, being able to handle characters, all of which have the exact same weight, was exactly the intent of the late 2005 and Farris in 83. Let me get some water, sorry. Okay, so a consequence of the criterion of maximizing homology is that the origination of two tails in separate parts of the tree is penalized more and more to the extent that the originating tails share more and more of their features, which is what we saw here. When you share many secondary features in the tails that are originating separately, it starts becoming preferable to consider the tails as homologs, which is a very sensible idea. Two tails which are originating separately, if they originate with all of their conditions in exactly their same shape, their same state, that would be very surprising, right? If the characters are really independent, you would expect that truly different independent originations of the tail would reappear with different combinations of character states in the secondary character. So if they are all the same, the stronger the grounds for considering those tails as homologs, which this criterion takes into account. Okay, so that's how the criterion in itself would work, because we are simply enumerating reconstructions. I am giving you some alternative reconstructions and we are evaluating those. So the problem is how you can actually find optimal reconstructions, right? Because you need to be able to do that. TNT takes advantage for finding optimal reconstructions of the fact that any set of characters can be converted into a set of Sankoff, that is, step matrix variables, obtaining perfect equivalence in results. Madison, and then Foray and Kitching and Brasseau, they had proposed that you can use Sankoff recoding, but the catch in Goloboff et al. And in Goloboff and Delete is that the costs for those step matrix variables are not arbitrary. Those costs follow exactly from the original character weights and transformation costs. Once you let maximization of homology for the original characters to enter the equation. And that maximization of homology for the original characters is what Madison never really had in mind. So that Sankoff supercharacter must have as possible states all the combinations of the characters and states included in it. More on this later. And the transformation cost between any two combinations of states must equal the sum of transformation costs between the original characters. So the idea here is, in a classic analysis, the ancestral morphotypes are the set of states for all the characters at every node. So you have your taxa where you have a bunch of zeros, zeros and ones, and that's what determines what the taxon is. And then you are going to reconstruct the characters one at a time for each of the ancestral nodes, right? That again is going to be a string of zeros and ones. In a classic analysis, every one of the characters is reconstructed independently of the others. And this morphotype is the sum of the individual states. But when there are dependencies between the characters, you cannot do that. You need to consider all of the characters simultaneously. So what you need is a method that allows considering the morphotypes as such, that is the entire ancestral condition. That is, the units of analysis should be the strings of zeros and ones that you can have. That sounds impossible, but it can be done relatively easy, thanks to the property of combinability of most parsimonious reconstructions. For any set of independent characters with their weights and transformation costs, it is possible to create an entirely equivalent representation of a single character, that is to say a variable, with many states and complex transformation costs. That is, there is a mathematical equivalence between both representations. So you suppose you have this matrix with, I think it's 10 taxa and 5 characters, 5 binary characters. So you have a bunch of zeros and ones. So you could, do you see the little thing that says you are sharing another screen, or that only I see that?
Just you.
Ah, okay. Because it was just over the thing I want to show. So because you have 5 binary characters, you can have different combinations of states. Oh, I'm sorry. Right? Those combinations will be everything is a 0, the last one is a 1, and so on. And you can enumerate all possible combinations, and 2 to the power of 5 is 32. You have 32 possible combinations, which are the possible ways in which the ancestors can be. Note that there are more states in this character than terminals. That's because the ancestors can be different to each of the terminals, and you need to consider those potentially different ancestors. So now what you would do is you go to the first taxon, A, and you say, okay, this has 00111, which is state number 7, 00111. Then you assign state number 7 for taxon A of this variable. Then you have B, which is 10100, and that corresponds to state 20. And then you complete all the entries for each of the taxa. And then you have a new matrix of a single character, right? In that matrix, in that single character with many states, you need to consider the transformation costs between the different states. If you go, say, from state number 7 to state number 20, you have to consider the differences in the original character. So you have a difference in here, another difference in this character, and another difference in this. So the cost of going from 7 to 20 must be 3. The cost of going from 7 to 25 must count all the differences in 4 characters in this case. So the cost from 7 to 25 is 4. By doing this for all combinations of states, you fill the entire step matrix. And then you can use that state matrix to do an analysis. Now, this character has many states, and we all know, I suppose, that the time required to calculate scores in step matrix characters is a lot of time. You can use algorithms by Sankoff and Rousseau for doing trees, and for saving time doing tree searches, you can use algorithms I published in 1998, but that time is always quadratic on the number of states. So as the number of states increases, the time you need to do the calculations increases pretty quickly, which means that the calculations themselves are slow. But even if they don't take the same time, one form of representation is going to be slower, but the two, this one with the binary characters and this one with a single character with many states and these complex transformation costs, they are going to produce exactly the same results. They're always going to choose exactly the same trees as optimal, the same differences in score between any trees, the same character mappings, the same group supports, and so on. So this is different algebra, but the same meaning. You are doing exactly the same thing, only using different calculations. Okay, now we get back to inapplicables, because I was just discussing standard characters. For characters that appear out of nothing, together with their primary characters, the cost must be a step. Say the tail originates twice, that's one step, right? Because two separate originations of the same combination imply a step of homoplasy, with the state in those two parts of the tree not being due to common ancestry. And this is going to be the case for every one of the dependent characters. This means that the cost of origination of combinations from, say, no tail to tail with many dependent characters must cost several steps. From no tail into a tail that is red, squared, and setose, the cost must be 4, because you are failing to homologize tail, red, squared, and setose, right? Now, if you have two separate tail losses, that fails to homologize a single condition, the absence of the tail. So the tail loss must cost a single step, because when you have no tail, the characters, color, section, and cover simply don't exist. So tails, gains, and losses must be in a ratio 4:1. Now, the important thing is that this is required for all homologies to have the same weight. This is asymmetric costs, but it does not mean an equal weighting. On the contrary, the asymmetry of the costs in the transformations between combinations of states is required to have a symmetric set of costs at the level of the original characters. And this is going to be the case when some characters cease to exist or come into existence in some cases. So if we look at some examples, I think this is clear. There's no going to be any problem with this. If you go from a tail that is red, squared, and setose into one which is blue, rounded, and scaly, that's going to be 3 steps. That's the cost that you should assign to the step matrix. So the problem is what happens when you go from no tail into a tail which is red, squared, and setose. If you want to think properly the correct way about the problem, think of a bunch of taxa with no tail, and think of what happens when in 2 different separate parts of the tree you have origins of a tail that is red, squared, and setose, right? How many similarities in the original characters are not due to common ancestry in that case? Clearly 4. 1 for the tail, 1 for the color, 1 for the section, 1 for the cover. Now, if you apply the same reasoning to the opposite transformation, you have a bunch of taxa, many taxa, which have a red, squared, and setose tail. And in 2 separate parts of the tree, you lose the tail. How many similarities in the original characters are not due to common ancestry? Clearly, just 1. Therefore, for every homoplasy in the original characters to have a unique cost, the cost from absence to presence in the primary character must be asymmetric, right? Now, further possibly difficult cases would be things like this. If the cost from no tail into a red, squared, and setose tail is 4, when you have 2 different originations of tails with entirely different secondary characters, that's going to sum up to 8 steps, 4 here plus 4 here. Okay? But if you have 2 separate originations of 2 identical tails, that's also going to cost 8 steps. Did we not say that this case implies this is not the same? There is homoplasy here, and there was no homoplasy in the case before, and they have the same scores. Well, yeah, you don't forget that you also have blue, rounded, or scaly tails, and they have to be somewhere in the tree. You need to consider those. So the complete picture would be this, and this would have 11 steps. So you have, in this case, 4 steps plus 4, that's 8. And from red, square, setose into blue, rounded, and scaly is 3 steps. So this has 11 steps, not 8. And the actual homoplasy must be compared against the minimum. What would the minimum be in a case such as this? Okay, you gain a tail of some color, section, and cover, and then you transform into that. This would have 7 steps. 4 steps here plus 3 here. And this is actually the minimum. There is no homoplasy in this case. Sorry, talking too much here. So, when you do 11 steps relative to the minimum 7, you have 4 steps of homoplasy, which is the right number. It is the number we had concluded from manual comparisons. So you always have the correct amounts of homoplasy being evaluated by the difference between the score and the proper minimum. If you have something like this, you see the change I'm making here, again, you also have 11 steps because you have the tail is a homoplasy between these 2, and the colors, the color, the section, and the cover are a homoplasy between these and those. And this is still the right number. The last detail to consider for using step matrix characters to handle inapplicable characters is the problem of the cost asymmetries and the root state. Suppose you have a tree like this where you have 3 tailless taxa, which are the successive sister groups of a group of things that has a tail that is red, squared, and setose, and it then later transforms into blue, rounded, and scaly. The transformation cost from no tail into the red, square, setose tail should be 4 steps, right? This would be an optimal reconstruction. You can reconstruct the character in this way, which would have 7 steps and no homoplacy. This would be 4 steps in here, right? Plus 3 steps in here. But remember that the transformation costs for the variable are asymmetric. Going from no tail into a tail costs 4 steps, right? So if you optimize that sunk off character on this tree freely, you are going to prefer this reconstruction because the tail starts as present and red and squared and set toes, and then it gets lost 3 times. So this would be 3 steps in 3 losses of tails, plus the 3 steps in here, it's only 6 steps instead of the 7 that we have for the actual no homoplacy. To solve that, what you can do is forcing the state in the outgroup, the first splitting taxon, to the root. So if you say the only states I can assign to the root are those which I observe in the first splitting taxon, then you switch to this reconstruction, which is always going to be the optimal one in terms of minimizing the homoplacy in the original characters. So TNT does this by itself. So the Sankoff approach, when does it have problems in the implementation in TNT? When you have not seen the outgroup taxon. Because in this case, I know it has a tail, or I will know that the tail is red and squared and set toes. But if I have not been able to observe the character in that taxon, then the evaluations of homoplacy in the implementation I have are going to be approximate. One could calculate the minimum and observed steps, both assuming that the primary is present and assuming that the primary is absent, those two, and then calculate the difference between observed and minimum and use the smallest. That is always going to be the correct amount of homoplacy. But I have not implemented that in TNT because it requires too many changes to my code for tree searching. So in TNT, homoplacy calculations for cases where the outgroup is unobserved for the primary character are only approximate, okay? One more point we discussed in Goloboff et al. 2021 is the calculation of minimum possible number of steps. The minima you need to consider, the minima you need to consider for having absolute values of homoplacy, right? As I showed in that difference between 11 minus 7. Now, those minima cannot be the possible minimum for the recoded Sankoff character because the recoded variable already contains all the conflict with it. Suppose you have a case such as these 3 standard binary characters. The best possible trees for this have 5 steps, right? This has 1 step for the first character, C and D go together, and 2 steps for the character that should join B and D, which are separate in the tree, 2 steps for the characters that should join B and C, which go separate in the tree, for a total of 5. If you recall this as a Sankoff character, there are 8 possible states, 4 of which are observed, and the minimum possible steps for these Sankoff characters is 5. The best tree you're going to find for this has 5 steps, which is correct because that is the length of the best possible tree. But the 5 steps tree contains homoplacy. We already know from looking at the previous example that there was homoplacy. So if instead of using the minimum for the recoded character, you use the minima of the original characters, the sum of the minima, then you obtain a reference value of no homoplacy of 3. And 5 minus 3 is 2, which is the correct value of homoplacy in this case. Therefore, TNT internally recodes the characters and uses a minimum value, which is a value that cannot be achieved on any tree when the data set has incongruent characters, which equals the sum of minima for the original characters, plus the cost of origination of the primary and secondary characters, if the primary is absent from the outgroup. With this, the calculations of homoplacy produce the correct absolute values and not just the right ranking of trees. Now, an interesting peculiarity of data sets where characters are not independent. The minimum total homoplacy can be obtained with different reconstructions which imply different amounts of homoplacy for the different characters. This is actually an expected consequence of having non-independent characters. The reconstruction in one character is connected to how other characters are reconstructed. Remember this case of ambiguity, right? Both reconstructions have 3 steps of homoplacy, but the one in the left has 3 steps of homoplacy by positing 1 step of homoplacy in the tail, 1 in the color, and 1 in the section. While for a total of 3, while the reconstruction in the right has 3 steps of homoplacy by positing only 3 steps of homoplacy in the tail and none for the colors. Okay. So there is also
Pablo?
some. ¿Sí? Yes.
¿Podemos descansar un ratito o te falta mucho? ¿Cómo estás?
I think, yeah, we're getting there, Santi. I was like closing this section, right? There was some discussion between Wheeler 2023 and Delete and Goloboff on, whether one should use events or not. Just read the papers. I'm not going to summarize that, but that's basically the only thing that has been published on inapplicable characters under parsimony after we published our paper. So this is the list of the most important papers, and in red are the papers which I consider give you like the right perspective, right? The other ones are papers you can, in my view, you can do without. Okay, so this will be part B, implementation and practice, right? We just finished with the theory, so we now get off the bus and move on to more practical questions of implementation, practical matters, and let's see some of the syntax and specification of dependencies. And this is what was defined in that paper with the LET in 2023. Something it may be important to know is that in the 2021 paper, which was where we laid out the first ideas on X transformation and using step matrices to handle inapplicable characters, we used in that paper the names of the characters themselves to establish the hierarchy of characters. So the superordinate and subordinate characters had to be called the same, right? You had to use the same name, but using sup and sub prefixes. Obviously, sub for superordinate character, and I wrote super twice, right? That should be subordinate, super and subordinate. TNT then would take the names of the characters and convert this into a new character, assigning the proper step matrix costs. I'm telling you this because there are some papers which actually used these conventions, but these conventions were limited to 32 states because this would convert the combination of characters into one standard character as in a matrix in TNT, so it was limited to 32 states, and it was rather inflexible in considering special cases because of that sub and sub prefixes, the nomenclature. So a few papers use this, but it's obsolete. So in the subsequent 23 paper, we removed those limitations using a syntax that is derived from the one in Anagalis. And the command is xlinks for character links. You must enable the use of xlinks prior to reading the data set. You normally do that as instructions in the data set itself. And then you first specify the primary character or characters with the states that determine inapplicability, and then within angles, the character that is inapplicable. You can use names or numbers for the characters and states. The only requirement for using names being that there is no ambiguity in the names. So you could say, for example, xlinks equal, and you use the equal for facilitating. That's like the option for defining the actual dependencies in xlinks. And then you say tail is absent. When the tail is absent, color inapplicable, section inapplicable, cover inapplicable. So the first one will be the primary variable, so to speak, independent if you want. And The ones within angle brackets would be dependent variables, so to speak, the consequences of the interaction, okay? And you indicate the inapplicable with just a dash. So with this, the entries in the matrix itself are just like in reductive coding. So you would be coding the tail as a 0-1 character, the color is a 0-1 character if you have only two colors, and a question mark when the tail is absent, right? Then you decide what the characters are, tail, color, and so on, and you score them as you see them when you can, or as a missing entry, when the character is unobservable. But the matrix would be exactly as in reductive coding, but you need to specify then, later, the dependencies between the characters. With the view links command, links, you show the combinations of states that TNT creates internally, which are really for your information. It's not that you need to know what those combinations are. You know that those are the combinations needed for maximizing homology, right? So TNT internally is going to create a character with 9 states. When the tail is absent, all the other characters are inapplicable, and then you have the combination. You can see that there are 4 reds, 4 blues, 2 and 2 and 2 and 2, and 1 and 1 and 1 and 1. That's all the possible combinations for the 3 characters. To view this, you use the command vlinks exclamation mark. TNT itself also calculates the step matrices, and as you can see, these step matrices are asymmetric, right? From no tail into different kinds of tails, the cost is 4. From some kind of tail into no tail, the cost is 1. To show the step matrices, again, it's not that you need to see this, but you may want to understand how the program is working. That's the vlinks equal option. Now, in the matrix, the dependent characters, color, section, cover, for example, must be scored as a missing entry in the dataset. They cannot be observed. TNT does not distinguish in the matrix between the symbols question mark and dash when it's reading alphanumeric data. But if you attempt to optimize, you can give TNT a matrix where you specify some color for a taxa which has been coded as having no tail, but if you attempt to optimize those trees for data sets that not comply that, you are going to get an error message, together with a list of the minimal changes needed for the data to obey the rules imposed by Xlink. So this is the kind of message you get. You are going to be told that there are illegal state combinations found in some terminals, and for example, in complex 0, for taxon 0, you need to change 0 into a 1. Right? Depending on what the character states are, you may need, because suppose you have scored color and section, what was the other one? The cover, the hairs or the scales, as something. Then you can either change those 3 into a missing entry or just the tail to be present, and that's a minimal change in this case. Okay. And then it tells you that you cannot optimize trees in that case, and alternatively, you can fix the matrix using vlinks pipe symbol. This is like the OR symbol in programming. But this will randomly select some character combination that fulfills the current rules. So from among the multiple possible, because in, for example, for taxon 9, you can either change the tail to be present or the color to be a missing entry. Either of those is going to be chosen at random by the vlinks, I don't know how to call that, pipe. So you can use that to quickly take a look at your matrix, but it's not the ideal. You really should go and fix the matrix. Of course, you can define different complexes of dependent characters. For example, you can say that when the tail is absent, the color, the section, and the cover are all inapplicable, and when the legs are absent, the clause in the fingers, and the spines in wherever are also inapplicable. So this creates internally two complexes, one for tail, color, section, and cover, and the other complex for legs, claws, and spines. You can link up to 32 characters in a complex, but the more characters that are linked, the more states the internals and cough recording requires, because you have to do all the combinations between characters and states. The exact number of combinations depends on the interactions between the characters, but generally speaking, running tree searches for more than a few thousand internal combinations, which is to say a few thousand states in the step matrix character, internal character, becomes really sluggish and requires a lot of RAM. And TNT is going to refuse to run complexes with more than 32,000 states, which is optimistic because you run out of time and memory well before. You may be able to run up to 4,000 or 5,000, maybe 10,000 if you're really patient. You can find out the number of needed combinations for analyzing your data with the Belling's double exclamation mark option. Belling's just one exclamation mark gives you the full list, but if you have thousands of combinations, you really are not going to study what those combinations are. You just want to know the number, and that you get with the double exclamation mark. All the cases we have seen so far have multiple characters depending on the same primary, but some of the secondary characters may in turn be primary to others, thus determining multiple levels of dependence. And that can be indicated by just listing the dependencies. Suppose then that you have a tail which can be red or blue, squared or rounded, killed or keyless, and can have or lack an apophysis. If it has keels, the keels can have a straight or bent contour. And the apophysis, if it's present, can have a smooth or grainy texture. So color, section, and keel and apophysis are inapplicable if the tail is absent. The keel contour is inapplicable if the keel is absent or inapplicable. And the texture, smooth or grainy, is inapplicable if the apophysis is absent or inapplicable. So you say, when the tail is absent, color, section, keels, and apophysis are inapplicable, and then you also say, when keels are inapplicable or absent, the contour is inapplicable, and when the apophysis is inapplicable or absent, the texture is inapplicable. That's all you need to do for a case like this. TNT alone is going to create the combinations of states, and if you look, I don't know, they're going to have a copy of this, I guess, Santi, right? So if you can sit down and look at the combinations, yes, you will see that those are all the legitimate combinations that you can have, right? Whenever the apophysis is absent, for example, the texture is inapplicable, and so on. And TNT calculates the step matrix costs for all the transformations between those combinations. Now, if you look more closely, you can see in that step matrix that in going from no tail to different kinds of tails, you don't always have the same cost. Sometimes you have more steps than in other cases. That's because those cases you can calculate from comparisons, but in those cases that depends on whether or not the secondary characters, which are in turn primary to others, are present or absent. Suppose you go from no tail into a tail which is present, red, square, and has no keels and no apophysis. The contour of the keels and the texture of the apophysis continue being inapplicable. Then the cost of transforming from state 0 into 1 is 5. But if you go into a state such that you have keels, right, then the contour is inapplicable, but there is some specific condition for the, what am I doing there? The keels. Oh, I got that wrong.
No.
Yeah. Yes, right. The apophysis is present, sorry, yeah. So the kills are absent, the apophysis is present, therefore you have the condition in the texture of the apophysis. If that originates in two separate parts of the tree, that smoothness is not going to be attributed to a homology. So that's one more case of homoplasy, and the cost for that is 6 if you really want to keep track of the homoplasy of the different reconstructions. And if you go to, say, state number 6, where both kills and apophysis are present, you are going to specify specific conditions. Oh God. Anyway, you're going to specify conditions for both the kills and the apophysis, and that would be 7 steps. So you have different costs of the transformation from no tail into a tail, depending on what happens with the secondary primaries, so to speak. Again, those differences are going to be needed for the original characters to be weighted equally, right? That is, to have every homoplasy in the original characters to cost 1. Then you have to have these differences in costs. And remember, the rationale is when a combination of states originates from the other into distant parts of the tree, how many cases of similarity in the original characters are not being accounted for by common ancestry. When the ending state in the original character originates twice, that indicates homoplasy. Now, it is entirely possible in the dependencies between characters that alternative states of a primary character make different secondary characters inapplicable. For example, consider the following characters. Character 0 is the skin, which can be smooth, scaly, or tessellate. Then, when you have scales, the scales can be smooth or keeled. And when you have tesselli, the shape of the tesselli can be squared or rounded. So what you need is that when the first character has this state, you can apply this one, but when the first character has this state, only this one is applicable. So the specification for that would be X-links, and when the skin is smooth or scaly, the tesselli are inapplicable, and when the skin is smooth or tessellate, the scales are inapplicable. Or even simpler, using the not option. So you say, when the skin is not tessellate, the tesselli are inapplicable. And when the skin is not scaly, the scales are inapplicable. With any of those specifications, TNT defines the possible state combinations automatically. And you can see in here, again, you see this with Belling's exclamation mark. So when the skin is scaly, the scales have states, but the tesselli are inapplicable, and when the skin is tessellate, the scales are inapplicable, and you can define what happens with the tesselli. Inapplicables that depend on multiple primary characters are no problem, and in this case, suppose you have the legs, which can have the anterior leg has a posterior apophysis on the posterior side, and the second leg has an anterior apophysis on the anterior side, and they can touch each other, and the character is the contact zone. Do they touch in full? Do they touch in part? Do they interlock? Whatever it is, that contact zone character. So if the posterior apophysis is absent, or that's what this symbol means in the TNT syntax, right? That means or the anterior apophysis is absent, then the contact is inapplicable. You cannot define how the interlocking between the two apophyses is if one of them is absent. Now, if both the anterior and posterior legs can themselves be absent, then the corresponding apophyses also become inapplicable when the leg itself is absent. So this might seem very complicated, but you simply say, when the leg 1 is absent, the posterior apophysis is inapplicable. And when the second leg is absent, the anterior apophysis, remember that's the one that is on the anterior face, the anterior apophysis is inapplicable. And then you also say that when the posterior apophysis is absent or inapplicable, or the anterior apophysis is absent or inapplicable, then the contact zone is inapplicable. With this, TNT creates all legitimate character state combinations and calculates the transformation costs. So that's easy to handle. Now, one more interesting problem is unobserved applicables. An unexpected property of the analysis of characters with regions of inapplicability is this. Suppose you have a tail that can be present or absent, and the color is applicable only when the tail is present, right? The typical case. But you have a bunch of taxa which have tails, but you don't know what the color is for those. Suppose they were scored on the basis of all photographs. Those are unobserved applicables. The character is applicable, but you don't know what it is. So you need to score that as a missing entry in the matrix. Now, if you have a tree like this, right, where you have all the red taxa connected, all the blue taxa connected, it's clear that this tree has no homoplasy. Now, suppose you place one taxon with a red tail in this tree. How many homoplaces are there in this case? That's 2 steps of homoplasy. One in the tail, one in the color, right? Suppose you place this back in here. Now you put a blue taxon in here. Again, how much homoplasy you have? 2 steps. One in the tail, one in the blue. Okay? Now suppose you put far away in the tree a taxon which has a tail, but for which you don't know the color. In that case, it is clear that there is 1 step of homoplasy in the tail, but what happens with the unobserved entry? What happens with the color? Well, there is no color observation here, so one may want to conclude no homoplasy, which is what one would do with standard characters. But the conclusion of no homoplasy would turn out to be right if in the future the taxon is observed to be, say, green, or yellow, or black, or white. But if that separately originated tail turns out to be blue, then that means 1 step of homoplasy in the color. And if that tail turns out to be red, when you can actually observe it, that's going to be 1 step of homoplasy. There is thus 2 options with separate originations of the primary character and unobserved locally applicable characters. You either count no homoplasy and assume that the unobserved applicable will have a new state different from all the other taxa in the data set, or you assume that the unobserved applicable will have one of the states observed in the other taxa, and then you are forced to count some homoplasy. So this is different from the interpretation of missing entries in standard characters, right? Because in that case, you can always postulate no homoplasy by assuming the same state in their ancestor. But how can you implement the no homoplasy interpretation in the case of inapplicables? Well, the way TNT does it internally is by assigning a new, different state to each terminal with a missing entry. And when you recode the data, you give it the same transformation cost from that new state into any other state or from other state. That really does the trick. In this case, the unique states do not need to be combined with all the other states in the data set, as discussed some slides back. I think it's some slides forward. Of course, assuming that the new state will or will not be observed in the taxon with a missing entry may be more reasonable for some characters than for others. Suppose assuming a new state for a DNA data set where you have already observed ACGT, then in that case, you cannot have a new state. You know that you will have homoplasy when you have an independent origination where you have not actually seen what the residue is. Therefore, TNT allows you to choose the interpretation to use for each character with the option that is X-links pipe, the bar symbol, with X-links bar 0 that counts a homoplasy for a missing entry, and with X-links bar 1 it doesn't. Now, all the recording and calculation of step matrices is internal in TNT, and the user does not need to know what's happening. I was explaining what happens because, well, you're taking this workshop, I suppose you're interested, but you really don't need to know that when we're doing specific analysis. On output, when mapping characters, TNT deconverts the sunk-off state combination into their original components and reports the results in terms of the original character. So it's going to show you this mapping. For example, for the case of the tail with the keels and the apophysis. So you start with the tail and you can see that there is only one character in the list here. But when you start having a tail, character number 3 would be the presence of apophysis, and therefore would be the presence of keels. Therefore, you have character number 5, the contour of the keels. And if you start traveling through the tree, you see that there are parts of the tree where you have more characters specified than in others. For example, in here, you only have 5 characters specified. That's because both, yes, 3 and 4 represent the keel and the apophysis. Because those are absent, characters number 5 and 6 don't exist. This is if you use states. You can also use the names of the characters, which of course it's a lot easier to follow. And TNT shows you the same kind of diagrams. Of course, they take a lot of space. So this would be the case where the tail is present, right? The color is red, the section is round, but there are no keels and no apophysis. So that is why there is no contour character or texture character as there is in other parts of the tree. We may want to skip this, right? How much time we have left? Like half an hour. We can go to the program.
There are questions, Pablo, if you want.
Okay, hold on. Give me 1 second. Okay, I have 2 slides for summary, right, of the commands.
Okay.
You get this with the help in TNT. I mean, if they are going to be able to watch this this presentation later, just want to let them know that they have those summaries in here, but you access those with help X links or help B links in TNT, so we can move to the program. Or, of course, if there are questions, let's do those. Yes, what are the questions? You have one data set in here. What I gave you, this is the part I said was going to be chaotic, right? When I'm doing the program, because it's not as structured as the PowerPoint. I gave you, in the materials I gave you, Denise, and the others, a bunch of data sets which illustrate different points I have been making and give you different examples of things, okay? I can open that with the notepad, and this one is called Inaps 5 2 parents. So this is exactly the example I showed. You can have anterior legs absent or present, posterior legs absent or present. The leg can support an apophysis only when it's thick. It's not that it's absent or present. I just made this up, right? So you define the links. Should I make this bigger? Or it's okay?
It's okay.
Looks okay. It looks fine.
Okay. And then you say, when the anterior legs are absent or they are thin or inapplicable, then the posterior apophysis is inapplicable. So either of those, this is 2 parents, right?
That's clear.
If you read this data set, I'm going to read it now. There is a version of TNT which is probably the one you are going to be using, right? If we read 2 parents, I tend to use a lot more the one with commands, because it's a lot easier for me because I remember the commands, right? But this is a list of, in here, if you go to data, character dependencies, it can tell you, I never do this, show current dependencies. Okay, so this tells me how the dependencies have been defined. Okay, so you can see that character 5 is inapplicable when you have this, and probably there's another entry for character 5. No, sorry, character 5 is inapplicable when anterior legs is absent, or this, I'm not finding it, should be further up. The point is, if you show the combinations, which you can do with data character dependencies, show state combinations, right? It's the same thing. You can see that if either the anterior apophysis or the posterior apophysis are absent, then the contact zone is inapplicable. Sorry, absent or inapplicable, right? So the contact zone can be defined as wide or narrow only when both the anterior and posterior apophyses are present. Of course, you could have chosen different states rather than presenting here, but this is depending on two things. Any of those two things which are not present, right, you get inapplicable for the last character. So yes, you can have two parents, you can have two primary characters, right? And remember that I showed, let's see, I told you that, let's make this a little bigger, this symbol, right? I mean, in different keyboards, it's in different places, right? But that's what stands for OR. If you want to say, because you might have a character such that when two things happen, not one or the other, they both have to happen, that would be an AND. And that comes to an AND. So if you say, that would be a different definition, of course, you could say, when the posterior legs are absent and the width of the posterior legs is this or that, then this happens. You can see the highlighting?
Yeah.
Yes.
Yes, it looks good.
Yes.
Okay. So the and the or can be used in here for specifying complex relationships. And there is a lot more that you can specify in here in addition to just inapplicabilities. I'm not going to save this. I'm just going to close it. So let's go to TNT. And, well, of course, I suppose you all know that to read the data file, you use this part of the menu, right? I'm going to just read whatever. This example, the first one, this defines, if we look at the data set, Sankoff equivalence, that is going to tell me that when character 0 has 0 or 1, then character 1 can have any state. That's what the missing entry is. That's why you need to remember. The dash is inapplicable when it is within the angles, and the missing entry means any possible state. Okay? And 2 can have any possible state, and 3 can have any possible state. This is going to do exactly the same recording I showed when I introduced the use of Sankoff recording and morphotypes. Remember? Every combination is valid. This is how you would recode into a single character a bunch of characters which are independent. If I read this with TNT, which is, I think, what I just did exactly, how many states should I have? Anyone wants to venture an answer? Didn't hear that? Let's look at the matrix again. The characters are binary, and you have 8 binary characters. So you can have, if you ask TNT to show you the character state, the character state combinations, show state combinations. That's 256. Remember that numbering starts from 0. Because 2 to the power of 8 is 256, right? So those are all the combinations in that recorded variable. I have included a script for you such that if you read this matrix, I'm going to read it by double-clicking. If you say, go to test, TNT shows you a sort of model tree because it's going to create a new character state matrix every time. And this is the matrix it created. It's almost at random because it has very long branches. Okay? So it first is going to analyze with an exact solution the original binary data, and it finds 3 trees with 15 steps. Then it's going to recode this as a single character which has 256 steps, right? And it does a search, it finds exactly the same 3 trees of 15 steps. Of course, it has to. There's a mathematical equivalence between both. It took 2 seconds because it's running just one character, but that character is very complex, right? TNT has the possibility, I skipped that part of the presentation, it's in the papers, of trying to get rid of those states in those combinations of states that you know will never occur in any optimal reconstruction. So you can get rid of some states, you only keep the ones you are sure you need, and therefore the analysis proceed much faster and use less memory. So that would be the third case that the script is showing you. If you type go to test again, then it's going, I think this uses a different random seed. So this would be the tree. Now the matrix is all different, right? And we found a set of different trees. I mean, it just happened to have, again, 15 steps. It doesn't have to. In every one of those cases, you can make the comparison of the results. In this case, we have a score of 17 steps. And we found 12 trees when we analyzed the characters as binary in the standard way. We found 12 trees when we consider all possible combinations. And we got 12 trees using a little less time when we considered only the combinations that I am certain I need, discarding some of those, okay? Now, you can disconnect what the script is doing, is in here. The X-links open square brackets and X-links closing square brackets connects and disconnects. This will be disconnecting, this will be connecting the use of the dependencies between characters. So right now we are using the dependencies, right? That's why we have 104 combinations of states needed to obtain optimality in the homology assessments. And if I go to characters dependencies, current dependencies enabled, if I do this, I deactivate the existing links between characters, so that if I say, show me the combinations, it doesn't give me anything. Sorry, I'm going to clear the screen so that you see, it didn't show anything because the links are inactive at the moment. So you can switch between the standard interpretation and the interpretation that actually considers the inapplicable characters very easily. Okay? So basically, once you define the links between the characters, which you can do by looking at the examples contained in the data sets which I have included here, right? Everything else proceeds transparently in the program. Okay, I have included, and the idea is that you can take a look more calmly after the workshop in your home. You can take a look to these data sets, and in about a month we can get together and check questions about the actual usage of all this. I included in here 3 empirical data sets which handle inapplicables. The titles of the data set tell you where the data set was taken from, right? So this defines a bunch of dependencies. I'm not sure where that is, probably at the beginning. Those are all the dependencies. I just use the numbers in there, right? So if I double click in here, now if I do data character dependencies count state combinations, right? That's simply going to tell me how many combinations I need to handle every complex. You can see that there are like 24 complexes in this case, because those are different parts of the animals, right? If I ask the program to tell me what the relationships between characters are, those are the ones. And you can see that there is one complex which comprises 11 characters, which has 656 states. So, for example, this one is going to take some time to run. So if I say run one replication of a Wagner tree plus TBR, saving a single tree, you can still see me. Are you seeing my finger?
Yes.
Okay. So we're doing the search there, but you can see that the search goes way slower than with standard characters. But that is the only way to take into account the interdependencies of 11 characters at the same time, right? So what's slowing TNT down a lot in this case is mostly that one character complex. So that's the time. We needed 20 seconds. It's still doable. It's still doable, but you can see how as you add more combinations of states, the search can really become very slow. So you need to be careful with how you do your searches. And in some cases, you may want to use some approximations. If some dependencies are not too important, you may decide not to take them into account in order to make the analysis computationally possible. So we're about done.
Pablo, I have a question, very practical question, just in terms of building the matrix. So in the matrix, the question mark and the dash is the same.
Yes.
It is only difference in the X-link definition is the difference.
Yes. Correct.
Okay. There's a question now.
Yeah, yes, sure. Now,
Shaki,
give me 1 second before we go to Shaki.
Yes.
Now, I gave you a PDF, right, which has assignments, so to speak, right? And this travels more or less through the examples we have been seeing in the presentation, right? And it asks you to do specific things using the program. I think if you know how to use TNT, for the rest of the things, you should be able to do those. And in any case, when we get together in a month from now, we'll try to solve problems.